A novel framework, Medical Decision Transformer, MeDT, leverages goal-conditioned reinforcement learning to recommend personalized treatment strategies for sepsis patients. By incorporating clinician input and interpretability, MeDT addresses the limitations of existing offline reinforcement learning methods. The framework utilizes a decision transformer architecture to learn a policy for drug dosage recommendation, conditioning on known treatment outcomes, target acuity scores, past treatment decisions, and current and past medical states. MED's offline training involves predicting administered treatments for each time step, capturing complex dependencies among a patient's medical history, treatment decisions, outcomes, and short-term effects on stability. The conditioning mechanism uses acuity scores to address sparse reward issues and facilitate clinician-model interactions, enhancing decision-making. By conditioning on desired positive outcomes, such as survival, and user-specified short-term stability improvements, MeDT can generate tailored treatment recommendations. The development of clinical decision support systems that assist healthcare professionals in making informed decisions is crucial, particularly in sequential decision-making tasks like evaluating a patient's evolving condition in the ICU. A key consideration is that the reward function employed by RL algorithms should ideally necessitate clinician input to ensure that the policy generates decisions aligned with the domain expert's intentions. Existing studies predominantly rely on binary reward functions, signifying the patient's mortality, which leaves no room for clinician input to modulate the policy toward achieving desirable tasks, such as stabilizing vital signs. In contrast, MED's framework enables a more interpretable, personalized, and clinician-directed approach. Rigorous experiments on the MICII dataset demonstrate that MeDT recommends interventions that outperform or are competitive with existing offline reinforcement learning methods. MED's approach highlights the importance of incorporating clinician input and interpretability in clinical decision support systems, particularly in high-stakes decision-making tasks like sepsis treatment. Reinforcement learning for sepsis treatment has been hindered by the limitations of recurrent neural networks, RNNs, in modeling complex and long medical records. Vanishing or exploding gradients result in suboptimal policies, while sparse rewards and sequential design exacerbate the problem. Furthermore, the low interpretability of model reasoning is a concern in high-stakes clinical decision-making. To address these challenges, the proposed MeDT framework utilizes transformers to model long sequences, enabling the learning of better representations for treatment histories and potentially yielding more informed predictions. MeDT is an offline reinforcement learning framework that recommends optimal treatment dosages by auto-regressively modeling a patient's state while conditioning on hindsight returns and one-step look-ahead patient acuity scores. This approach enables the learning of more effective and interpretable treatment recommendations. The framework consists of a transformer-based policy network that models the full context of a patient's clinical history and recommends medication dosages. Additionally, MeDT allows clinicians to guide the generation of treatment decisions by specifying short-term target improvements in patient stability. The proposed framework outperforms or is competitive with popularly used offline RL baselines over multiple methods of off-policy evaluation. In contrast to existing works, MeDT does not assume a baseline reward of 0 until the end of treatment, but instead considers shorter-term objectives, such as the stabilization of vital signs. This approach addresses the limitations of existing works and provides more effective and interpretable treatment recommendations for septic patients. Related work in reinforcement learning for sepsis treatment has explored the use of value iteration algorithms, Q-learning, and model-based RL to provide personalized, real-time decision support. However, these approaches often overlook the importance of shorter-term objectives and the need for interpretable model reasoning. In contrast, MeDT provides a more comprehensive approach to reinforcement learning for sepsis treatment, enabling more effective and interpretable treatment recommendations. In the realm of healthcare, particularly in intensive care units, ICUs, treatment modeling is a complex task due to the partial observability of patient states and the challenges posed by sequential data processing. To address these issues, the proposed MeDT model leverages transformer-based policies that can better capture long contexts and process information in parallel. This approach integrates self-attention mechanisms to identify dependencies between distant time steps, enhancing decision-making capabilities. MED's architecture builds upon the deep treatment (DT) framework, which conditions a policy on the full history of states, actions, and an observed or desired reward to go. MeDT further improves this by incorporating short-term goals for patient vital signs, leading to more effective sepsis treatment recommendations. The MeDT training process, as depicted in Figure 1, involves attending to the past treatment trajectory at each time step T. This includes desired treatment outcomes, desired next step acuity scores, patient states, administered drug doses, and outputs a dose prediction. This approach helps in identifying the most relevant aspects in the treatment history, which may not be immediately apparent. Off-policy evaluation, OP, is a crucial problem in reinforcement learning, RL, that involves estimating the expected return of a given decision policy using historical data obtained by different behavior policies. This strategy is particularly useful in situations where interacting with the environment is costly, risky, or ethically challenging, such as in healthcare. However, OP is inherently difficult due to its requirement for counterfactual reasoning. The autoregressive evaluation pipeline, as depicted in Figure 2, leverages a pre-trained state predictor to generate predictions of patient states at each time step T. This predictor integrates past recommended doses, initial patient states, and predicted patient states to output a prediction of the patient state at time t+1. Both dosage recommendations and predicted states are fed back to MeDT to simulate treatment trajectories with multiple sequential decisions. Off-policy evaluation, OP, plays a pivotal role in learning optimal policies. OP methods, such as importance sampling, weighted importance sampling, WIS, fitted Q evaluation, FQE, and weighted doubly robust, WDR, estimation, are employed to evaluate policies based on historical data. These methods aim to adjust the weight of each episode or experience to estimate the evaluation policy's value accurately. IS and WIS methods use validation data to assess the evaluation policy's value by adjusting the weight of each episode based on its relative likelihood. WIS is considered more stable than IS. In contrast, FQE predicts the expected cumulative reward for taking a specific action in a given state, rather than adjusting weights. WDR combines importance sampling and value estimates at each step to improve accuracy and reduce variation. Approximate models, AMs, involve directly modeling the dynamics of the environment to evaluate policy performance. While this approximation may not be exact, it can provide sufficient policy evaluation. Empirical results demonstrate that FQE provides the most accurate and stable estimations over varying data conditions. Interpretability is a crucial aspect in safety-critical fields such as healthcare. Despite extensive research, the deployment of deep learning in healthcare has been met with resistance due to the black box nature of these networks. Attaining interpretability in reinforcement learning, RL, has been a major challenge. The authors acknowledge the need for interpretability and the limitations of current methods in this regard. The deployment of reinforcement learning, RL, algorithms in real-world applications, particularly in safety-critical domains like clinical decision-making, is hindered by their complexity and lack of interpretability. Traditional methods for understanding transformers, such as visualizing attention weights, have been shown to be limited in accurately capturing the relevance of input tokens. Alternative methods, including the rollout method and layer-wise relevance propagation, have also demonstrated limitations. To address these challenges, the authors employ a generic interpretability method based on information flow, which has been shown to produce more accurate interpretations while being simpler to implement. They frame the problem as a Markov decision process, MDP, comprising a tuple of patient states, possible dosage recommendations, state transition function, reward function, and next patient state. The authors utilize offline RL, which learns an optimal policy using a fixed dataset of collected trajectories, to mitigate the risk of direct interaction with the environment. The proposed medical decision transformer, MeDT, architecture follows a similar approach to DT, using transformers to model offline RL via an upside-down RL approach. The input tokens for the policy model encode past treatment decisions and patient states, as well as the desired return to goal, RTG. The output at each time step is a distribution over possible actions. The model is conditioned using RTG, which represents the singular positive or negative treatment outcome at the last time step, similar to DT. Additionally, the authors propose conditioning MeDT on short-term goals, such as future patient acuity scores or achievement of therapeutic goals, ATG. The SAPS-2 acuity score is used due to its consideration of relatively more physiological variables, providing an indication of the severity of the patient's illness in the ICU. This novel approach enables the MeDT architecture to make informed decisions based on both long-term and short-term goals, enhancing its interpretability and effectiveness in clinical decision-making. MeDT is a framework that enables clinicians to interact with a model to generate treatment dosages for sepsis patients. By incorporating a more informative conditioning scheme, clinicians can input desired acuity scores for the next state, providing additional context for treatment selection. The SAPS-2 score is broken down into constituent scores, representing the status of specific organ systems, to enable more detailed inputs. This allows domain experts to establish and select a scheme for interpretable short-term goal conditioning, guiding the model using their knowledge of the relation between intermediate goals and favorable long-term outcomes. The treatment progress over T time steps forms a trajectory, which is used to train a causal transformer network to predict ground truth dosages administered by a clinician at each time step. The policy aims to learn an optimal policy distribution, ignoring future information and the prediction target via masking. The model architecture uses an encoder with linear and normalization layers for each input type, capturing temporal dynamics using learned position embeddings. The learned policy is evaluated in an observational setting using a model-based off-policy evaluation approach. An additional predictor network, based on the causal transformer, is introduced to learn a state prediction model. This allows modeling how a patient's state changes in response to medical interventions and enables inferring estimates of patient acuity scores from predicted states. The estimated acuity scores provide clinically relevant estimates, indicating how the stability of the physiological state of the patient may change given a treatment policy. The predictor network is trained to learn the distribution p theta, street, a less than t, s less than t, using a similar architecture as the policy network. The estimated acuity scores can be used for policy evaluation, and during inference, the model allows autoregressive prediction of future patient states. This enables evaluating the learned policy in a simulated environment, without interacting with real patients. The evaluation approach is based on the model-based OPE approach, suitable for healthcare applications where interacting with real patients is unsafe. The learned policy is assessed based on historical data, and the estimated acuity scores provide clinically relevant estimates of patient outcomes. This evaluation approach enables evaluating the learned policy in a realistic setting, without compromising patient safety. Algorithm 1 outlines the evaluation loop for assessing policy performance in sequential decision-making processes. It takes as input the initial patient state S0 and outputs the acuity score G1, GT for each time step. The process starts by setting the target return RT equals 1 initializing the state S1 equals S0 target return R1 T equals RT and action sequence A0 equals The algorithm then enters a loop, where at each time step T the desired acuity to go KT is selected, and the action at is determined using the MeDT function, which considers the current state S1, T action sequence A0, T1 and target return R1, T The action at is appended to the sequence of actions, and the new state street plus 1 is estimated using the state estimator function. The acuity score GT plus 1 is then evaluated for the new state street plus 1 The algorithm also utilizes three evaluation methods: weighted importance sampling, WIS, weighted doubly robust, WDR, and fitted Q evaluation, FQE. WIS uses a behavior policy pi b to evaluate a policy pi by reweighting episodes according to their likelihood of occurrence. The WIS estimator is computed using the per-step importance ratio rho t and cumulative importance ratio rho 1 t. FQE is a value-based temporal difference algorithm that utilizes the Bellman equation to compute bootstrapped target transitions from collected trajectories. The FQE estimator is computed using the estimated Q function hat wide Q pi of policy pi . WDR combines both value estimators from FQE and importance sampling from WIS to reduce the overall variance of estimations. The WDR estimator is defined as a weighted sum of the importance sampling estimator and the FQE estimator. The evaluation loop continues until the final time step t , at which point the acuity score G1, GT is returned. Figure 2 and Algorithm 1 illustrate the rollout procedure, which generates a sequence of actions by predicting how the patient's state evolves as a result of those actions. Equations 4, 5, and 6 provide the mathematical formulations for the WIS, FQE, and WDR estimators, respectively. These equations demonstrate the use of importance sampling, value-based temporal difference learning, and weighted doubly robust estimation to evaluate the performance of policies in sequential decision-making processes. A comprehensive evaluation of various reinforcement learning algorithms, including the proposed medical decision transformer, MeDT, was conducted on a challenging septic patient cohort. Table 1 displays the estimated final patient acuity scores, averaged over 2,898 patients, for 7 different models: BCQ, NFQI, DDQN, CQL, BC, DT, and MeDT. MeDT achieved competitive performance with state-of-the-art models, with an overall score of 40.31 plus or minus 0.03. To assess the interpretability of MeDT, a transformer interpretability method based on the principle of information flow was employed. This approach computes relevance scores to visualize the importance assigned to input tokens. The method involves propagating relevance maps through the self-attention layers of the decoder transformer architecture, using attention matrices and gradients to update the relevance scores. Aggregated attention scores are calculated, and the resulting relevancy scores can be visualized as a heat map. To adapt this method to MeDT, relevance scores are normalized based on the receptive field of attention. The experimental settings for MeDT are described in section 4.1, outlining the training and evaluation procedures for MeDT on a cohort of septic patients from the MICII dataset. The dataset comprises 19,633 patients, with 8,773 septic patients used for training and 2,898 for testing. MED's performance is evaluated using various metrics, including estimated final patient acuity scores. The computation of relevance scores and the adaptation of the transformer interpretability method to MeDT are mathematically formulated in equations 7 to 9. Equation 7 initializes relevance maps as identity matrices, while equation 8 defines aggregated attention scores using the attention matrix and gradients. Equation 9 updates relevance scores using aggregated attention scores. These mathematical concepts underlie the interpretability of MeDT and its ability to provide insights into the decision-making process. The results and methods presented demonstrate the effectiveness of MeDT in handling complex decision-making tasks in healthcare, while providing a framework for interpreting the model's decisions. The use of transformer interpretability methods enables the visualization of relevance scores, crucial in understanding the model's decision-making process and identifying potential biases. The proposed MeDT approach is evaluated on a real-world dataset of patients with sepsis, characterized by a mortality rate of 9%. This dataset undergoes preprocessing according to the pipeline defined by Killian et al. 2020, involving the extraction of physiological measurements, imputation of missing values using the nearest neighbor algorithm, and averaging multiple observations within each 4-hour window. The patient state consists of 5 demographic variables and 38 time-varying continuous variables, including lab measurements and vital signs. The administration of vasopressors, VP, and IV fluids is discretized into 5 bins, resulting in a combinatorial action space of 25 possible treatment administrations. MeDT is compared to several baselines, including BCQ, NFQI, DDQN, and CQL, which are commonly used algorithms in offline reinforcement learning. Additionally, 2 transformer-based algorithms, DT and a transformer-based BC, are trained and evaluated. MeDT differs from DT in that it conditions on acuity to go at each time step, in addition to returns to go. The transformer policy is trained on mini batches of fixed context length, randomly sampled from a dataset of offline patient trajectories. A context length of 20 is chosen, which is the longest patient trajectory in the dataset following preprocessing. Trajectories shorter than this length are adjusted using zero padding. During training, teacher forcing is used, where the ground truth sequence is provided as input to the model. At each time step t, the actual acuity score of the state at time step t+1 is used to set the acuity to go ATG value. The prediction head of the policy model is trained to predict the corresponding discrete treatment action using a cross-entropy loss. The loss for a complete trajectory is averaged over time steps. The state estimator is separately trained to predict the patient's state following the treatment actions. The prediction head of the state predictor model is trained to estimate the continuous state using a mean square error loss. The models are trained on NVIDIA V100 GPUs. Experimental results are aggregated to evaluate the performance of MeDT and the baselines. The evaluation metrics used include FQE, WIS, and WDR off-policy evaluations, which are visualized in Figure 4. The box plots show the performance of MeDT and the baselines across different evaluation metrics. The results indicate that MeDT achieves competitive performance with the baselines, demonstrating its effectiveness in optimizing treatment policies for patients with sepsis. The authors evaluate the proposed MeDT network in an autoregressive inference loop with a state predictor, comparing it to multiple baselines. The average and standard error of SAPS-2 scores for every patient in the test cohort are calculated, with results presented in Table 1. The MeDT policy, conditioned on both positive RTGs and a chosen ATG heuristic, yields the most stable estimated patient states. In contrast, the DT framework, conditioned only with positive RTGs, performs better than baselines BC and others. Performance analysis by sepsis severity level reveals that MeDT results in more stable states for low and mid-severity patients, while DT performs best for high-severity patients. This suggests that MeDT requires more samples to reach convergence due to the additional ATG context. Figure 5 visualizes 4 patient trajectories computed by the state predictor following treatment recommendations from DT and MeDT. Sample efficiency evaluation, presented in Figure 9, shows that DT performs better when trained on 50% of the data, while MeDT is performant on 75% and 100% splits. This supports the hypothesis that the additional conditioning used in MeDT has a negative impact on sample efficiency. Off-policy evaluation methods, including FQE, WIS, and WDR, are used to assess policy performance, with results presented in Figure 4. MeDT produces the highest estimated values on FQE and WDR, while CQL performs best on WIS. Notably, MeDT and DT policies exhibit less variance than baselines, indicating they are more robust models. These results suggest that the clinical dosage recommendations based on the proposed conditioning method may have had the intended treatment effects. The findings indicate that MeDT and DT policies can effectively estimate patient states and provide stable treatment recommendations, with MeDT performing well for low and mid-severity patients and DT performing best for high-severity patients. However, the additional conditioning used in MeDT may compromise sample efficiency. The use of off-policy evaluation methods further validates the performance of MeDT and DT policies, demonstrating their potential for robust and effective treatment recommendations. The relevancy maps in Figure 6 illustrate the importance assigned by the model to input tokens when predicting action A5 for a sample patient trajectory. Darker and lighter colors indicate lower and higher relevance scores, respectively. By taking the mean of the relevancy assigned to the ATG components, The heat map effectively visualizes the relevance across time, highlighting the importance assigned to each conditioning. A qualitative analysis evaluates the MeDT policy against the clinician's policy using ground truth trajectories as input sequences. Figure 3a presents a comparative analysis of the mean dose of vasopressors and intravenous fluids recommended by the MeDT policy and the clinician policy for patient states with varying SAPS-2 scores. The results show that the MeDT policy generally aligns with the clinician's treatment strategy, recommending lower doses of intravenous fluids on average. Both policies exhibit a similar trend of increasing medication doses with worsening patient condition for both vasopressors and intravenous fluids. However, the MeDT policy uses more zero-dosage instances for both intravenous fluids and vasopressors compared to the clinician policy, likely due to the imbalanced nature of the dataset, where over 91% of patient trajectories resulted in positive outcomes. Notably, the MeDT policy diverges from prior research by refraining from recommending minimal dosages for patients with elevated acuity scores, indicating better generalization and sample-efficient properties. Figure 5 visualizes the trajectories of multiple patients computed by the state predictor, following treatment actions recommended by both the DT and MeDT policies. The impact of ATG conditioning on patient health is evident, as MeDT leads to more stable trajectories, demonstrating the potential of the framework to generate targeted and improved treatment recommendations. However, some patient trajectories show that the MeDT policy produced the same or worse action policies relative to DT, with no discernible effect of ATG conditioning, which may be due to limitations of the dataset. Despite this, the alignment with the domain expert policy is ideal, particularly in this high-stakes task where the algorithm relies solely on pre-existing static data for learning. In high-stakes applications like healthcare, the interpretability of reinforcement learning (RL) algorithms is crucial. Current RL algorithms often function as opaque systems, making it challenging to understand the specific data features influencing a suggested action. To address this, the MeDT model, a novel RL approach based on the transformer architecture, provides interpretable and interactive intervention support systems for clinicians. The MeDT model assigns relevance to input tokens, allowing clinicians to monitor the specific points in time when the model assigns the highest importance. This is visualized through relevance plots, such as Figure 6, which shows the relevance assigned to each ATG component over time. By considering the conditioning for the hepatic of higher relevance in its prediction, the model facilitates an assessment of its reasonableness. By providing insights into the model's decision-making process, clinicians can identify potential errors and assess the reliability of the recommendations. If the model differs from ground truth clinician actions, an analysis can reveal which features carry the most weight in the decision-making shift. This not only enhances understanding of the model's decision process but also invites future research into the reliability of deep RL decision-making from a clinical perspective. The MeDT model is trained using a combination of hindsight rewards and look-ahead patient acuity scores at each time step, enabling clinicians to guide its treatment recommendations by conditioning the model on short-term goals for patient stability. An autoregressive evaluation of the proposed approach is presented using a separately trained state predictor that models a patient's clinical state evolution given a sequence of treatment decisions. Experimental results demonstrate the potential of MeDT to bolster clinical decision support systems by providing clinicians with an interpretable and interactive intervention support system. The model's ability to provide insights into its decision-making process and facilitate clinician interaction is a significant step towards addressing the limitations of current RL algorithms. Reinforcement learning has been increasingly applied to various healthcare problems, including sepsis treatment, critical care, and sequential medical treatments. The decision transformer, a sequence modeling approach to reinforcement learning, has been a key contribution in this area, enabling the modeling of complex sequential decision-making processes. Its extension, the generalized decision transformer, has further improved offline hindsight information matching. Interpretability is crucial in reinforcement learning, particularly in high-stakes applications like healthcare, where insights into the decision-making process are essential. Offline reinforcement learning has been explored as a sequence modeling problem, with methods like offline policy evaluation and batch policy learning under constraints being developed. Imitation learning has also been applied to optimize sequential medical treatments. In the context of healthcare, reinforcement learning has been used to optimize sepsis treatment, with studies demonstrating its potential in improving patient outcomes. Additionally, reinforcement learning has been applied to optimizing sequential medical treatments, such as personalized medicine and treatment planning. The importance of interpretable reinforcement learning methods cannot be overstated, as they provide insights into the decision-making process, enabling clinicians to make informed decisions. Furthermore, offline reinforcement learning methods can learn from existing datasets, reducing the need for online exploration and improving the safety and efficiency of reinforcement learning in healthcare. This section of the research paper delves into a comprehensive overview of various transformer models and their applications in reinforcement learning, particularly focusing on healthcare scenarios such as sepsis treatment. Citing numerous studies, the authors demonstrate how transformers have been utilized to enhance language understanding and decision-making processes in complex environments. The paper begins by referencing Tianyang Lin et al.'s 2022 survey on transformers, which provides an in-depth analysis of these models' capabilities and limitations. It then moves on to discuss the use of transformers in healthcare, specifically highlighting their potential in improving sepsis treatment strategies through reinforcement learning. In this context, the authors mention Mingyu Liu et al.'s 2020 work, which evaluates the readiness of deep reinforcement learning for practical applications in healthcare. This study assesses the sensitivity of dual DDQN, a deep reinforcement learning algorithm, for hemodynamic management in sepsis patients. The findings suggest that while there are promising results, further research is needed to ensure the reliability and efficiency of such algorithms in real-world settings. The paper also explores the potential of transformers in enhancing the efficiency and effectiveness of reinforcement learning algorithms in healthcare scenarios. By leveraging the capabilities of transformers to process sequential data efficiently, researchers can develop more sophisticated models that learn from experience and adapt to changing conditions. Moreover, the authors emphasize the importance of addressing challenges associated with applying transformer models in healthcare, such as data scarcity, model interpretability, and ethical considerations. They propose several strategies for overcoming these hurdles, including the use of transfer learning, multimodal fusion, and transparent model architectures. Overall, this section of the research paper presents a detailed examination of transformer models and their potential applications in reinforcement learning, particularly in the context of healthcare and sepsis treatment. The authors provide a comprehensive overview of existing studies, highlighting both the opportunities and challenges associated with utilizing these models in real-world scenarios. Reinforcement learning, attention mechanisms, and clinical decision support systems are crucial components in machine learning and artificial intelligence. In reinforcement learning, mapping rewards to actions is essential, rather than predicting them, as emphasized by Jürgen Schmidhuber. Attention mechanisms, as researched by Sophia Serrano and Noah A. Smith, require transparency and explainability to ensure effective decision-making. In healthcare settings, learning from uncertain concepts via test-time interventions, as demonstrated by Ivaksisheth et al., and model selection for offline reinforcement learning, as explored by Shengpu Tang and Jenna Wiens, are vital. Richard S. Sutton and Andrew G. Barto's introduction to reinforcement learning highlights its significance in decision-making processes. Reinforcement learning has numerous applications in healthcare, including septic shock resuscitation, as researched by Nicholas Simpson et al., and consensus definitions for sepsis and septic shock, as defined by Mervyn Singer et al. Clinical decision support systems, as overviewed by Reed T. Sutton et al., offer benefits, risks, and strategies for success. Factored action spaces in offline reinforcement learning, as demonstrated by Shengpu Tang et al., and vision transformer methods for deep reinforcement learning from pixels, as evaluated by Tianxin Dao et al., are also crucial. Off-policy evaluation, attention mechanisms, and transformers in time series analysis are essential in reinforcement learning and artificial intelligence, as highlighted by researchers such as Philippe Thomas, Emma Brunskill, Masatoshi Uehara, and Ashish Vaswani. These concepts are instrumental in advancing machine learning and artificial intelligence in healthcare and beyond. The MeDT model, despite its advantages, has limitations and areas for future improvement. One major concern is the geographic bias introduced by the MICII dataset used for training the state predictor. To address this, the authors suggest exploring causal representation learning and pre-training techniques to enhance model robustness. An ablation study was conducted to compare the performance of DT and MeDT models on patients with negative and positive ground truth trajectories. The results show that DT performs better on patients with negative trajectories, while MeDT exhibits improved performance on positive trajectories. This disparity can be attributed to the conditioning of RTG in DT and the larger number of positive samples available for MeDT to learn from. Additional visualizations of patient trajectories generated by the state predictor following treatment recommendations from both DT and MeDT models were provided. These visualizations highlight instances where MeDT produces the same or worse recommendations compared to DT, potentially due to dataset limitations. The MeDT model's transformer architecture consists of 6 layers, trained with batch sizes of 64 and a learning rate of 0.0006. Utilizing the JELU activation function. Looking ahead, the authors propose that the MeDT framework has potential scalability for developing systems that provide effective treatment recommendations for other medical conditions in the future. Figure 7 visualizes 6 patient trajectories computed by the state predictor, contrasting treatment recommendations from decision tree, DT, and modified DT, MeDT, algorithms. This graphical representation highlights potential variations in patient responses based on distinct decision trees employed within the decision support system. Figure 8 presents the average training validation performance curve of the state predictor model, derived over 10 experimental trials to assess reliability. This curve quantifies the efficacy of the state predictor in minimizing errors across unseen patient data and forecasting treatment trajectories based on historical cases that formed the dataset used for training. Table 2 compiles an exhaustive list of 34 patient attributes that form the state space considered in the research, encompassing demographics, baseline clinical characteristics, and treatment parameters. These attributes include age, gender, Glasgow Coma Scale, vital signs, comprehensive metabolic panel, blood gas analysis, coagulation profile, liver function tests, and specifics of fluid management. This comprehensive set of attributes allows the model to capture nuances in patient responses to different treatments. The combination of figures 7 and 8 demonstrates the efficacy of the state predictor in forecasting treatment outcomes and adapting to changing patient conditions. The reliability of the model is crucial in making accurate predictions, evident in the consistent performance curve. This study emphasizes the importance of integrating diverse attributes in patient data to make accurate predictions about treatment outcomes. Figure 9 illustrates the performance of MeDT versus DT on scaling from training on 50% to a 100% of the trained split, averaged over 3 seeds. MeDT consistently outperforms DT in terms of accuracy and stability across different training sizes. Table 3 details the observations considered for the split SAPS-2 scores, categorizing them into organ systems such as cardiovascular, respiratory, neurological, renal, hepatic, hematologic, and other variables. This comprehensive list highlights the multifaceted nature of the physiological parameters used in the study. Table 4 presents an ablation study on patients with ground truth positive and negative trajectories. The table compares the performance of 3 models BC, DT, and MeDT when adding or removing certain variables. The findings suggest that MeDT exhibits superior performance compared to both BC and DT, demonstrating its effectiveness in handling missing data and improving predictive accuracy. The research emphasizes the importance of considering multiple physiological parameters and utilizing robust machine learning algorithms like MeDT to predict patient trajectories accurately. By leveraging a wide range of variables and addressing missing data issues, the study contributes to the advancement of clinical decision-making systems, potentially enhancing patient care and outcomes.